Picture this. You're holding a newborn's head. It's so soft, you feel like a strong breeze could leave a dent. Yet inside that delicate dome, billions of wires are finding the perfect ports. How on earth does something that squishy build circuits with GPS-level accuracy? Here's the thing. The brain doesn't just follow chemical breadcrumbs, it also listens to touch, tiny pushes and pulls we never feel. And the star of today's story is a molecular pressure gate called piezo-1. First, what is piezo-1? Think of it as a front door sensor on every young neuron. When the surrounding tissue gives the cell membrane even the slightest nudge, piezo-1 pops open, ions rush in, and a set of genes flips like light switches. Those switches tell axons, go left, slow down, make a turn. In other words, the brain's texture chats directly with the wiring crew in real time. Now, you might wonder, how big are these texture changes? Honestly, they're almost comical, going from squishy to just a hair less squishy over a space thinner than a grain of salt. But neurons and their glial sidekicks don't shrug that off. They sample the ground every few microns, then tweak their internal scaffolding to stay on course. When scientists mapped those micro-landscapes, they found tenfold jumps in stiffness hiding inside those tiny distances. Let that sink in for a second. A tenfold difference inside a salt grain width. No wonder cells pay attention. To see how much this matters, researchers built artificial playgrounds, hydrogels whose softness they could dial like a volume knob. A mere step from very soft to moderately soft tripled the levels of certain axon guidance messages within hours. That's like your GPS rerouting 3 times just because the asphalt changed grade. But a living embryo isn't static. Blood vessels sprout, ventricles inflate, glial fibers stretch. So the mechanical map today is different tomorrow. Early arriving neurons read one set of force lines and lay down broad highways. Latecomers read a slightly tweaked map and add local side streets. Same address, different directions depending on when you check in. What happens if piezo-1 can't hear those whispers of force? In animal studies, normal graceful pathways turned messy, detours, dead ends, axons overshooting their targets. Genetic work in humans hints that some neurodevelopmental conditions may stem from exactly this problem. The chemical cues are there, but one half of the conversation, mechanical sensing, is garbled. Engineers are already borrowing this trick. In the lab, they sculpt mechanical maps into soft biomaterials, no extra chemicals needed, and herd stem cell neurons along preferred routes. Imagine brain-on-a-chip devices that use gentle force patterns instead of complicated growth factor cocktails to test new drugs. The same concept is creeping into regenerative medicine. Carefully tuned implants or injectable gels could nudge injured circuits to reconnect along safe lines instead of wandering off course. Cancer researchers are even asking whether tumors hijack these subtle shifts to choose invasion paths. Fast forward a decade. You walk into a clinic, and instead of just a brain scan, you get a mechanical fingerprint. Tiny sensors map how your cortex bends and resists, spotting weak zones before symptoms surface. Therapies might then tweak forces, through smart helmets, sound waves, even customized pillows, gently steering cellular choices the way city planners reshape traffic by redesigning intersections, not by adding more road signs. Let that image hang for a moment. So here's what we covered today. 1. A pressure gate called piezo-1 lets neurons feel the brain's texture and flip genetic switches on the fly. 2. Even minuscule changes, from soft to just slightly firmer, create tenfold stiffness differences that cells treat like road signs. 3. Lab experiments prove it. Tweak softness and guidance messages triple within hours. 4. In living embryos, the mechanical map keeps shifting, which means timing is everything for growing circuits. 5. When the system breaks, wiring goes haywire, but that same knowledge is helping engineers guide neurons, design regenerative gels, and dream up future diagnostics that tune forces instead of chemicals. Here's the empowering part. The next breakthroughs in brain health might come not from new drugs, but from learning how to whisper the right mechanical cues. Soft pushes, gentle pulls, the kind you'd never feel, could one day fine-tune recovery after injury, or even prevent miswiring before it starts. Thanks for listening. If this episode got you thinking, share it with someone who'd love a fresh take on how our brains quite literally feel their way into shape. Until next time, stay curious and keep sensing the world around you.